Excellent. Okay, so where we left yesterday, we defined three principal stresses, okay, being sigma 11, sigma 22, and sigma 33. We said all of them are normal stresses. And we also said if we think about the Earth, then we can replace them as sigma V, sigma capital H, and sigma small h. What does that mean? That out of these three stresses, three principal stresses, where there are no shear stress, okay, sigma V, one of the stresses is vertical, and other two are horizontals. And all three of them are mutually perpendicular to each other. Okay. Now, if we look at the surface of the Earth, okay, what we will observe. So, say if you are standing exactly at the surface of the Earth, okay, at that place, sigma V is equals to sigma capital H is equals to sigma small h is equals to 0. Okay. So that means at the very top, at the surface of the Earth, there are no stress, or it is a stress-free surface. So the surface of the Earth is a stress-free surface, or we call it just a free surface. Okay, there are no stresses just at the surface of the Earth. However, with depth, all these three stresses keep on increasing. How do they increase? We will discuss in a moment. But before that, let us try to see what is the actual reason for such stresses. Okay? What are the reasons for such stresses? So stress means force per unit area. So we have to understand the reason behind the forces that essentially uh, puts stress on the earth at different points. Okay? So we need to see what are the forces that act here. Mechanical forces, of course. Okay. Now let us think of and pay very good attention here. Okay. This is a very important concept not only for geophysics. Uh, it will stay with you for the rest of your life if you are practicing geology or earth science or earth and environmental science. So pay extremely good attention. There are many people, I mean, who are accomplished geologists, but I fail to, when I interact, I fail to see that this particular concept is not clear. Okay, so make sure that you pay extreme attention. And this is very easy, so it should not be a difficult deal as well. Suppose we are thinking of the layered cake stratigraphy of the Earth. So this is the surface of the Earth, of course. And then as we are going down, we have increase in depth, right? So let us put some numbers. Okay, say this is 500 meter, 1000 meter, 1500 meter, 1000 meter, and 2500. Now let us say I want to know the stresses at this point T. Okay. I want to know what are the stresses acting. So I want to express E. I want to express SV, S capital H, and S small h at point P. Okay, that is my job for this particular exercise. So the first thing we have to understand, what are the forces acting on this particular point P. Okay. So can someone just tell me, just by looking at it? Of course, all these rock layers, say this is rock layer A, rock layer B, C, D, E. Yeah, it could be anything, any rock, and all of them will have some sort of density. Row one, row two, row three, row four, row five. Here I have essentially used the same H. I mean, in all these cases, my thickness of individual layers I have kept same, but it will of course be different in a real situation, right? So I have different thicknesses of different rock layers which have different densities. Okay. Now, if I ask you, what are the forces that are acting at this point P? Can someone just tell me? You can unmute and tell me what is the from your mind. What is the force that you can think of which is acting on this point P? Anyone? Use your common sense and tell me.
So the weight of all the layers above.
The weight of all the rocks. Excellent. That's the first thing. So we have the first force is weight of all the rocks. Okay, as simple as that. Yeah, absolutely. Of all the rock layers above. So that weight. What else? What are the other forces that you can think of can act on this particular point P? So the weight of the rock, if I try to put a kind of a vector around it, so the weight of the rock will essentially act. So if we say weight of the rock is, say we assign it as W. Okay, so the weight of the rock, the direction of the weight of the rock will be from top to bottom, right? This is how the weight acts, right? You agree with me? Okay. So now you tell me, what are the other forces you can think of?
Maybe a normal force from the rocks below the point opposing the weight.
Um, that is there, but I mean, this point, I mean, that will not negate the weight of the rock, right? So
Yes.
the action has its reaction, but it will not negate the weight of the rock. Okay. Anything else? What else?
Sir, fluid pressure.
Fluid pressure. Excellent. Why are you saying fluid pressure? Can you elaborate that a little bit? You have said it right, but can you elaborate that? No?
Sir,
Yeah.
pressure due to fluids accompanying that layers. Maybe oil or
Okay. Okay. Yeah. So say for example, all these layers, just for the sake of argument, we say these layers are porous and permeable, right? So there is grain, and then there is of course either water or hydrocarbon in all these layers. So for the sake of simplicity, let us say this whole thing is filled with water. Okay, so the pore spaces of this where is the blue one? I don't see the blue colored pen. Anyway, so let us say this is water. Okay, every molecule in between is like, so there is like a water column uh, sitting up. Okay, everywhere there is water, so there is a pressure from the water. Okay, so fluid pressure. Now you have to tell me how fluid pressure is different from the weight of the rock in terms of their anisotropy. So do you think weight of the rock is anisotropic and fluid pressure is isotropic, or vice versa? What is your idea? So okay, so you can see, of course, you can imagine that the weight of the rock will be anisotropic, okay, because it's not coming only from one direction, anisotropic. And fluid pressure, if you think about it, that perhaps, I can imagine that, P is like sitting like a balloon, okay, which is also filled with some sort of water, okay, some sort of fluid. We have said this is water, and the fluid pressure will act from in to out, okay, like this. But this is also isotropic. Fluid pressure will act in every direction with equal amount, okay. Now, if I think of about the weight of the rock vector and the fluid pressure vector, they will be opposite to each other. Okay? They will be oppositely directed. So weight of the rock, so W and P are oppositely directed. Because fluid essentially, it's thinking of that there is a balloon which is filled with some sort of fluid, maybe water, and then you are trying to press the balloon. So when you are trying to press the balloon with the weight, the water which is inside is trying to push you off. Right? So higher the fluid pressure inside the balloon, it is more difficult to press the balloon. Right? So we have got two forces. One is the weight of the rock, the other one is the fluid pressure. What is the third force that can work here? Tell me. Let's just draw the fluid pressure here. What is the third force that will work here? Tell me. You know about this.
If there is movement between the layers, there will be shear.
What is that?
If there are movements between the layers, then there might be shear.
Why? I mean, why would there be movement between the layers?
Tectonic activity.
Tectonism, absolutely. So plate tectonics. Okay, and we know plate tectonics works in the horizontal direction, right? So I can put plate tectonics. So there is force from all these directions, okay, with different amount. Okay, so this is plate tectonics. Now think about this point P. Okay, imagine that you are standing here. You are standing here, yeah, and you are kind of squeezed inside the rock. You are kind of squeezed inside the rock. Okay, now I'm trying to push you from the top. Okay, if you did not have rocks around, okay, no problem. You'd take the weight, and you will get compressed, so on and so forth. But then there is resistance from the rock. Okay, so by the weight itself, so as you are trying to press something from the top, and if you are confining it from outside, so there will be also forces acting in the horizontal direction for the vertical force, right? So for the vertical force, I will also have horizontal resistance. And for the horizontal force, I will also have, by the same logic, I will have the vertical resistance. Okay. And as you can see, all the weight of the rock and the plate tectonics are trying to essentially towards P, and the fluid pressure is away from P. Okay. So all these three factors essentially provides you the stresses. The weight of the rock first thing, the plate tectonics the second thing, and the fluid pressure, which actually acts opposite to weight of the rock and plate tectonics. Okay. So now you can imagine that, so all these three forces would act at this particular point. And if we so you know, if I now try to put that in bit more perspective, this is what I want to mean. So this is, suppose I have, let me just draw a cube properly. So here my weight of the rock is coming. Okay. Because I have the weight of the rock, this is trying to expand in these directions. Okay. Then I have plate tectonics coming from this side in all sorts of sides actually. Then because it is coming from this direction, it is also trying to get expanded in the vertical direction. And then there is an interplay of forces happening. And not only that, I also have the fluid pressure, which is trying to negate these weights, right? So if I now do a complete kind of vector analysis, okay, I mean, if I do a complete subtraction and addition and subtraction, what I will be left with, you know, a force which is coming from the vertical direction, okay, a force which is coming from all sorts of horizontal directions, but one of them is maximum, and there will be another direction which is minimum. And what you will observe, that maximum direction and minimum direction is mutually perpendicular to each other, and there will of course be different you know, what is that called, weights from all directions, sorry, different forces from all directions, but they will be of intermediate values. So I have got the forces. So now if I just simply subdivide it in divide it by the surface area, what I will get? Stresses. Okay. So then what I can write down, stress will be, so SV is nothing but the weight of the rock by area. Okay, that is my vertical stress. S capital H is after doing all that thing. So the maximum horizontal force, maximum horizontal force divided by area, and S small h is minimum horizontal force by area. So I've got SV, S capital H, and S small h. So these are what we call as total stress They are all principal stresses. Okay. Now, say the fluid pressure, we call it as PP, or this is also called pore pressure. And we said that the pore pressure acts in the opposite direction to the stress. Then we can write down something called SV effective is equal to SV total minus pore pressure. S capital H effective is equal to S capital H minus pore pressure. But remember, this pore pressure and this pore pressure are the same at a particular depth. And S small h effective is equals to S small h minus pore pressure. Okay. So this S V effective, S capital H effective, and S small h effective are called effective stresses. Effective stress is nothing but the total stress minus the pore pressure. Okay. So now, if I ask you then to draw how SV, S capital H, and S small h will change with depth. So what I have to do, and I'm trying to draw a graph where in the x-axis I am plotting pressure or stress, same thing, because the units are same. Let us plot it in bar, and then depth is in meter. So this is zero depth. This is zero depth. So what do you think? Where would the where at zero depth? So let us first try to draw SV. Okay, let us first try to draw the SV curve in the pressure depth plot. Okay, so where do you think SV will be at 0 meter? Tell me someone. I'm trying to draw the total stresses. Where SV will be at 0 meter? I mean, at the surface of the earth, where would SV be? Come on. What would be the value of SV at the surface?
0.
0, absolutely. We said that. That is why we call it a free surface, right? So it will start with 0. Okay. And we said, how do I calculate the weight of the rock? You know, I have these individual layers. Rho 1 and its density is rho 1 is its density, H1 is its thickness, rho 2, H2, rho 3, H3, rho 4, H4. Okay, these are my individual layers. Okay, so if I do a summation of rho GH, okay, I will be able to find out my SV. Okay. If I do a summation of rho GH, I will be able to find out my SV. So for that, what I will need? I will need the individual thicknesses and their corresponding average densities. Okay. So what people have generally seen, but this is not a perfect value. So if you want to get the actual value of SV, you have to go with this process by calculating rho GH. Okay, summing up rho GH for individual layers. But then a normal, an approximation is SV has a gradient of 2.26 per 10 meter. Okay. So with that gradient, I can draw a straight line. This is my SV, which has a gradient of, so this is approximation, huh? This is approximation, 2.26 per 10 meter. So if I ask you to calculate, say for example, say this is at 3000 meter. If I ask you to calculate the value of SB at 3000 meter. What I have to do, I have to simply go here, right? Remember, this SB what we are talking about is total stress. Okay, I have not yet subtracted pore pressure from it. So 2.26 bar per 10 meter. So 0.226 multiplied by 3000 would give me a value of SB at 3000 meter. Okay, but that's an approximation, as I said. Here, if I want to essentially calculate the actual value of SB, then what I have to do, I have to go, from surface to 3000 meter, then I have to see how many rock layers are there, and then what are the average densities and thickness of those layers, and then I have to do a summation. Okay, then I will be able to calculate my SB in a more robust way. Is that clear? Is that clear, everyone? Can someone just confirm it is clear with you?
Yes, sir.
Okay, excellent. Now, is capital H is generally 80, sorry, around 75 to 80%, around 75 to 80% of SV. Okay, S capital H is generally 75 to 80% of SV. So I can draw S capital H here. Around 75 to 80% of SV. That is also increasing with depth. And S small h is generally seen to be, 65. S small h is around 65 to 70%. So I can draw S small h. So SV is vertical stress, S capital H is maximum horizontal stress, and S small h is minimum horizontal stress. And I can calculate the value of SV, S small h, and S capital H by using these simple formulas. Now, in this particular example that I am giving you, what I am saying that SV is more than S capital H, more than S small h. And this sort of configuration is called normal stress regime. Okay? This is called normal stress regime. There are two more stress regimes which we will understand better when we do structural geology, but then just let me give you the definition of them. There is another stress regime which is also pretty much there in the earth, where I see S capital H is more than SV, more than S small h, and SV is actually intermediate. So that is what we call as the strike slip stress regime. And then there is another one where S capital H, SV is minimum, and that is what we call as reverse stress regime. What are they? Why do they occur? We will discuss about them later on. Okay. For the time being, let us restrict our discussion only for the normal stress regime, where SV or the vertical stress is maximum. Okay.
Sir, in
So this
the
is
plot, the depth versus pressure plot,
mhm.
is it always necessary that the relation is always linear like this?
Not necessarily. There is they are actually not linear. Okay. The real data will show you that they are asymptotic at a depth. Okay, but for the timing you don't have to worry about it. Okay, for the timing you consider them to be linear. Linear stress gradients are good approximation for the time being. Okay, when we study structural geology, when we get into the actual details about such stresses, we will see that they are not linear. Okay, they will vary, they will be asymptotic, but for the timing, linearity is a very good approximation for you to remember.
Sir,
Okay,
also the densities, are we considering some particular pattern in them, or like constant density or any random density?
no, in if you are doing an approximation, you are considering constant density.
Okay.
Okay, it's like the effect of all the densities. Okay, but if you want to do a better job, if you want to do a more robust job, of course the densities will vary. Basalt and sandstone will not have the same density, right?
Yes.
So then you have to take the actual density of that particular rock, whatever is there. I mean, it's not about assumption; it's about the real value of the density.
Yes, sir.
Okay, so that will of course then deviate your linearity. It will change the linearity of the curve. The linearity is an approximation. Okay, and you will of course see S small h is a actually behaves, because you have asked. Now S small h actually behaves something like this. We take another. Which color shall I take? So S small h actually behaves something like this. So at the very top part, it's goes like this. Looks like something like this. It's asymptotic. Why? We will discuss later on. For the time being, I don't want you to be bothered about its non-linearity. Okay?
Okay, sir.
Because there are other reasons which is beyond the scope of the discussion right now. Okay? But remember that linearity is a good approximation. Yeah. At least if you are taking a segment, now say for example, I'm taking this segment, I can think it to be linear.
Okay.
So now we have got SVS capital H and S small h, and this is based on normal stress regime. Of course, if I change my stress regime, the position of these curves will flip. Right? You understand that. Now then there is pore pressure or the fluid pressure. So let us draw the fluid pressure with a color blue. Okay, because blue is the color of the water, and then pore pressure will also change. Pore pressure, and that changes around 1.15 bar per 10 meter. Okay. So this is for 1.15 bar per 10 meter is for a normal brine. This is for normal brine. Why brine? What do I mean by brine? Brine means salt saturated water, or the water which has dissolved salt. Okay, so if you completely saturate the underground water, okay, and it's you cannot saturate any more salt into it, okay, dissolve any more salt into it. In that case, the fluid pressure goes all the way up to 1.19 bar per 10 meter or so, and it's for complete fresh water which doesn't have any dissolved salt into it. Then the pore pressure is 1 bar per 10 meter because of the density of water. Okay, so 1 bar per 10 meter is for fresh water, and 1.19 bar per 10 meter is for completely saturated with salt, that sort of brine. Okay, and a normal value, a general value, reasonable value is around, an average value is around 1.15 bar per 10 meter. That is the pore pressure. Okay, and sometimes you will see, and why does that happen? We will discuss later on. Sometimes you will see that the pore pressure also makes jump. It follows the same gradient, but sometimes you see pore pressure makes a jump over some layers. Why do that happen? We will discuss later on. And this is what we call as overpressure. Okay. The thing becomes bit more complicated though when it is not water. Say for example, yeah, that this particular depth, from here to here, I have gas. Okay, I don't have water. So I will not be able to go with this gradient. Below, the gradient will remain constant. I'm showing it in the overpressured example, but it can happen here as well. I mean, it can happen in the hydrostatic pressure gradient as well. So this is called hydrostatic gradient, okay? Right. So in that case, say for example, what is the gradient for gas? For gas, the gradient is around 0.2 bar per 10 meter. Suppose this is from where I have gas. So what I will observe, my pressure will do something like this. Okay. And then again, it will flip back to original normal. Okay. So this is how the pressure should have changed, but it is now following this path. And the pressure will get a bit more complicated. Okay. Now, if I want to calculate effective stress at any point, the effective stress will be, say, effective minimum horizontal stress at any depth. The effective horizontal stress maybe at this depth will be, minimum horizontal stress will be, this is the total minimum horizontal stress, total SH, small h, and this is the pore pressure then because of the overpressure. Okay, so then TSH minus PP will be your effective horizontal stress. Effective maximum horizontal stress, I have to go this value and then subtract it from PP. Effective vertical stress, this value and subtract it from PP. Now, if I am here at this depth, okay, this depth D1, this was D2, that is what we have calculated. At D1, my minimum horizontal stress is here, my pore pressure is here. So my effective horizontal stress will be this value x minus y. So that is how we define stresses. Any questions so far before we get into another topic which is called strain? Any question? Or is it clear? If it is clear, I am delighted. Then you have actually understood the, the pressure system of the Earth, at least the crust.
Sir,
How
could
does
you
it?
repeat the S small h and S capital H difference?
No, what I said that calculating effective stress, right? What is the definition of effective stress? Is total stress minus pore pressure, right? So
Yes.
total stress I will get from, it depends on which total stress I am trying to calculate. If it is effective, say for example, I'll give you another example. I mean, let me do it once more. Suppose I want to calculate my total stress at point D. Okay, so what I will do, the total vertical stress will be at point X, right? The total maximum horizontal stress will be at point Y, and total minimum horizontal stress will be at point Z, right? You agree with me?
Yes.
Now, what is the pore pressure at that point? The pore pressure will be here at point say M along the hydrostatic gradient. Okay. Now, if I want to calculate effective stress, I will have to do X minus M or Y minus M or Z minus M, right?
Yes.
Similarly, if I am here, at point D2, this is my total vertical stress. This is total horizontal stress. This is total minimum horizontal stress. And because of the overpressure, this is where my pore pressure, right?
Yes.
So then SB will be the difference between this point and this point. I mean the effective SB. Effective S capital H will be difference between this point and this point. And
Yes.
effective minimum horizontal stress will be this point minus this point, right? Now, if I am at D1, similarly, I can calculate SB here, total SB here, total S capital H here, and total S small h here. But the pore pressure, because of the gas gradient, has shifted here, right? So the pore pressure will be here at this point, Y. And then I have to then do the same subtraction. This minus this will be my effective stress at D1, effective vertical stress at D1. This minus this will be my effective vertical stress at effective maximum horizontal stress at D1, and effective minimum horizontal stress is this minus this. Okay, simple. So this gradient has changed simply because instead of water, this gradient has changed because instead of water, I have gas here. And this gradient has gone up because I have overpressure.
So what is the overpressure like? Is it because
Overpressure means, say for example, sometimes the so why we do see such beautiful gradient coming up, because the pressure actually equilibrates, right? If
yes.
in a particular layer the pressure cannot equilibrate with the surrounding, in that case there are reasons for that. Say for example, very quick burial of a layer, okay, then the fluid cannot interact with the surrounding or interacts with a very slow rate in geologic time. In that case, the pressure is actually little bit enhanced, and that is the reason for overpressure.
Okay.
Okay. So now, because this has become too clumsy, let me just draw it in a fresh graph. This is pressure. This is depth. SV. Is capital H.
Sir, also one more doubt regarding the
Yeah.
SH, capital H and small h. So in
Yeah.
so is it like, or the in real life the horizontal stress can be any plot which goes through between the S capital H and S small h plot?
No, one have to be maximum, one have to be minimum, right? So there could be a horizontal stress which is neither maximum nor minimum. But then that is not a principal stress. What we are only dealing here with principal stresses.
Okay. Yes.
These principal stresses are only three.
Yes.
Okay, so yes, of course, there will be a horizontal stress which is between S capital and S small h. That's what we said. But
But
but that is not we are interested in. We are interested in defining the principal stresses.
right.
Okay.
Yes, sir.
And here is my S small h. Here is my hydrostatic gradient, pore pressure, yeah, which can actually be shifted with an overpressure. So this is how it was supposed to go, but it is actually jumped. So this is overpressure. Okay, and then I can also have, because of the presence of a different fluid, I can have a different gradient. So this was supposed to go like this with the overpressure, same overpressure, the same jump. Okay, this gradient, and this gradient are the same. Just a total change in the pressure. Okay, but then you can see here that the pressure is actually following a different gradient along this red line, and this is because of the presence of any other fluid, be oil or gas. Or gas. This is the normal hydrostatic gradient. This is the OP, means overpressure. Okay, and at any point, if I want to calculate my stresses, what I have to do, draw a line. Total vertical stress P is X is total vertical stress, Y is total maximum horizontal stress, Z is total minimum horizontal stress, and M is pore pressure, X minus M. X minus M is effective SV. Y minus M is effective what? Y minus M is what? Tell me, someone. Y minus M is what?
Effective SH, S capital.
Effective S capital H. And Z minus M is effective small h. Okay, and that I can do at any depth. Okay, suppose if I want to do it at this depth, is X, Y, Z, and this is pore pressure. Okay, and then I have to do the same. If I do it here, X, Z. Is it clear? I thought I will start with strain today, but it doesn't look like I can. Anything is not clear? Tell me. You can read any book. I mean, I told you to read about structural geology by S.K. Ghosh for stress and strain, but then you will never find it written the way I have talked about it. Okay, so make sure. I mean, there is no book where this is explained in such a what should I say, in a simple way. So it is your chance or time to ask questions if it is not clear. And if you want to continue with the physics part of the earth science, this is something which you must know, and have absolute no confusion about the stresses and the pressure of the earth. Okay, so I will just end today's lecture by introducing another important concept. Okay, I will give you two real life examples. Okay, so I give you one chalk here. This chalk is with Kavin, and the other chalk, the chalk 2, exactly same, huh? There is no difference. Don't get into my drawing, my bad drawing, but they are exactly same two pieces of chalks. One is with Kavin and another with Sivats. Okay. I asked Kavin to actually, just push it from one end to break it. And Srivats is trying to break it with the same force from here. But maybe Shivangi is actually trying to hold the chalk, is holding the chalk from the other sides. Which one do you think is easier? Which one do you think would break quickly? The Kevin's chalk or Srivats' chalk? Which one would break quickly? More quickly. You understood two situations, right? In one, I am only pressing it from one side, and in the other one, I'm pressing it from one side with the same force, but also holding it from all other sides. Which one will break quickly? Tell me, Sivats, will your chalk break quicker than, earlier than Kavins, or Kavins will break fast? Sivats, tell me. Kevin's chalk will break. And why do you think that is? Why do you think this? Why do you think that is? Okay. So whether a rock will be deformed or a material will be deformed actually depends on not the absolute value of stress. So the deformation, I have one more minute, I'll just say. Deformation is not dependent on the absolute value of stress. It is dependent on something called differential stress. Okay, let us say this is SV and this is SV as well. And all this, you are doing it isotropically. This is S small h, you are holding it from every side with a small h. Okay, so SV minus S small h is called differential stress. So higher the value of the differential stress, yeah, quicker it gets deformed. So here S small h was actually 0. Yeah, in Kevin's case, S small h was actually 0. But then in Srivat's case, S small h had some value. So SV minus S small h was smaller than Kevin's case. So differential stress essentially guides deformation, okay, not the absolute value of stress. So, and differential stress is nothing but the difference between the maximum stress and the minimum stress. Differential stress is the value, um, is the difference between maximum stress and minimum stress. Okay. So with that note, I will open the floor for one more minute for any question, and otherwise I'll just, yeah, differential stress lower means lower deformation. So say for example, if I have a chalk and I can make a situation where I provide gigantic forces from all sides, but they are absolutely equal and differential stress is 0, the chalk will remain intact. Nothing will happen to the chalk theoretically.
Sir, in the differential stress formula,
Yeah,
can the S capital H come? Like, subtraction.
No, S capital H is not the minimum stress. Na? Referential stress is also always the difference between the maximum stress and the minimum stress.
Okay.
Intermediate stress doesn't play a lot of role here. Okay, we will see that why later on. I mean, later in your in next semester. But for the time being, remember intermediate stress, which is S capital H, doesn't play a big role in controlling deformation.
So
It's
this,
always the maximum stress and the minimum stress and that difference.
so this formula applies specifically for normal regime.
Any regime, I mean, yeah, for if it is for reverse regime, then of course it will be S capital H will be maximum and SV will be minimum. It's still the difference between S capital H and S, that then the difference will be S capital H and SV. Yeah, that is true.
Thank
So
you, sir.
maximum stress and minimum stress, whatever are there, yeah, the difference between them guides the deformation, not the absolute value of stress.
Yes.
Okay, remember that for the rest of your life. Okay, so if you can create a situation, maybe you can think of an egg, okay, which is very easy to break. Okay, but theoretically you can create a situation from where from all sides you provide exact amount of stress. Okay, so that the differential stress is zero. Now, if you keep on increasing your absolute stress from all sides to gigantic values, I mean, it will still not break because the differential stress is zero. Okay, so differential stress is something that guides deformation, not the absolute value of stress.
Yes, sir.
Okay, anything else? Okay, if not, I will stop it here. I will upload the pre-recorded lecture tomorrow. Thank you.